Chapter 3 continues our Chapter 2 look at interest rates and moves to security valuation, stocks and bonds. Interest rates can be measured in different ways and referred to differently. Coupon rate refers to the annual rate paid on a bond. Required rate of return is, as the slide says, the rate investors used to calculate the fair value of an asset's present value. Think CAPM. Expected rate of return is the rate an investor expects to earn. Realized rate is the rate that is actually earned. Let's look first at required rate of return. This should look familiar from 331. It's the basic formula for the fair value of a financial asset. The present value of its expected future cash flows. Remember, the tilde over the CF indicates expected, discounted at an appropriate rate, R, the required rate of return, for the number of periods in that the cash flows will occur. Example 3.1 from the text. A Walmart bond. Bought it 2 years ago for $890. Now it's selling for $925. The coupon is $100 a year, and you expect this to continue. You plan to hold the bond for 4 more years, and you think you can sell it then for $960. Your required rate of return is $11.25. Since you know N is 4, you can use the basic formula from the previous slide to find the present value, $935.31. Or you could use the TVM keys on your calculator. Given the present value of $935.31 and the selling price of $925, the bond is undervalued. I know, this looks just like the last couple of slides, but this is expected rate of return. Expected by you. Required was required by the market. Same basic formula, same cash flows, but now the discount rate is the expected rate of return. Back to the Walmart bond. Same info, but now we're solving for the expected rate of return by solving for the rate that makes the $100 cash flows over 4 years equate to the current price of $925. Solving the given equation, the expected rate of return is 11.607. You can do this in your calculator. With the required return of 11.25 versus an expected return of 11.607, again, the bond is undervalued. Finally, the realized rate of return. Same formula, but now we're using the actual purchase price. Here we'll use the actual purchase price and the realized cash flows to solve for the realized rate of return on the next slide. Walmart, one more time. Same bond. You bought it for $890. It pays $100 a year in interest and is currently selling for $925. We're solving for the realized rate of return over 2 years using this data. Remember, you got $100 the first year and another $100 the second year, plus the $925 selling price. Result, $13.08 realized return. And again, you could solve this in your calculator. This should look very familiar from 331, the basic bond valuation formula. Recall, a bond's value is composed of the present value of the annuity of its coupon payments plus the present value of its face value. We'll be using the TVM keys on your financial calculator to value bonds. As with all the TVM functions, Excel has functions comparable to each of the TVM keys. Also recall from 331, while we start out valuing annual payer bonds, bonds all pay interest semi-annually, so some adjustments to the calculations have to be made. Everything inside a red box has to be divided by 2. The discount rate, which is quoted as an APR, so you can just cut it in half, and the coupon payment is adjusted to a 6-month payment. The items in blue circles are multiplied by 2, the number of periods to maturity. Recall, everything has to be adjusted to 6-month periods, so years to maturity has to be doubled to get the number of 6-month periods to maturity. This just repeats the needed adjustments relating them to the TVM keys involved. Multiply years by 2. Divide the nominal yield to maturity by 2. Divide the annual coupon by 2. And there it is. Example 3.4. You're considering a $1,000 face value ExxonMobil bond. Coupon rate's 10%, paid semi-annually or $50 every 6 months. The bond matures in 12 years and the required return, yield to maturity, is 8%. You can see the formula solution, but more likely you'll use your calculator. Pay attention to the adjustments made. N is equal to 12 years times 2, 24 6-month periods. IY is 8% divided by 2, 4%. The payment is $100 a year divided by 2, $50 every 6 months. Also remember from 331, if a bond's required return, yield to maturity, is less than its coupon rate, the bond will sell at a premium. It's paying a higher rate than currently required in the market for bonds of similar risk and maturity. If a bond's required return, yield to maturity, is more than the coupon rate, then the bond will sell at a discount from its face value. If the bond's required return equals its coupon rate, it'll sell at face value at any time during its life. We just went over how to compute the price of a bond, but in truth we can observe the price. What we cannot observe is the yield to maturity, but we can imply it from the known values. The yield to maturity is the rate of return required on bonds of similar risk and maturity. You can find this with your calculator by entering the N, PV, PMT, and FB and solving for IY. Remember the sign convention. Payment and future value are positive. Their inflows to you. Present value is negative, the price you pay to purchase the cash flow stream of interest and the face value. Moving from valuing bonds, the easier task, to valuing stock. The easiest, a stock with a dividend that is not growing. Basically, this is the preferred stock formula. D is the permanent dividend amount, R is the required return, P is the price. More common is the constant dividend growth model or the Gordon growth model. The assumption is that the firm's dividend will grow at a constant rate G each year forever. D0 is the last dividend paid, so it's observable. Given the required return on the stock, RS, we can find the current value of the stock. Note the numerator. D0 times 1 plus G is equal to D1. So the two versions are the same. When working a problem, be careful whether the given data is the dividend just paid, D0, or the next expected dividend, D1. Taking both of these equations we just covered, zero growth and constant growth, we can solve them algebraically for the required return. Zero growth on the top and constant growth below. Again, note the two versions of the constant growth model. While we're usually trying to find the current value of the stock, the basic equation, this same equation can and will be used to find the value of a stock at any point in the future, time t. Since the dividend grows at a constant rate, and we know D0, we can find any dividend in the future. Moving on to the realized rate of return on a stock. Same basic formula pattern, but we're replacing the expected cash flows with the realized cash flows, and the required rate of return with the realized rate of return. Example 3.5. You have owned stock in General Monsanto for 2 years. You bought it for $25 a share and you just sold it for $35. Stock paid an annual dividend of $1. You can see the formula solution on the slide. Realized return, 22.02%. Using your calculator is much easier. Expected rate of return used expected cash flows and the current price to find the expected rate of return. Example on the next slide. This time you're considering Hewlett-Packard stock. You expect to own the stock for 3 years. The current price per share is $32 and you expect to sell it for $45 in 3 years. You also expect a $1.50 dividend per year. Using the formula, we find the expected return of $16.25. Using your calculator, we find the same. Example 3.8 covers finding the price of a stock which has zero dividend growth, basically preferred stock. Constant dividend is $5 a year, required return 12%. Easy to find the price is $5 divided by 12%, $41.67. Examples 3.9 and 3.10 deal with stock with a constant rate of dividend growth. Example 3.9 finds the stock price. You're looking at J.P. Morgan stock, which paid a $3.50 dividend last year. That would be D0, its history. The constant growth rate is expected to be 2%, required return is 10%. Using the constant dividend growth or the Gordon growth model formula, shown to the right, we find a stock price of $44.625. Example 3.10 finds the expected rate of return for a constant growth stock. In this case, you're looking at Bank of America stock, which paid a $4.80 dividend last year. Again, D0. Dividend growth is expected to be 1.75% per year. Stock's currently selling for $52. Converting the constant growth formula to solve for return and solving, we find a return of 11.14%. The most complicated case is when the growth rate is not constant. In this case, Home Depot is experiencing supernormal growth of 10% a year for 5 years before stabilizing at 4% forever. Remember this from 331? We can combine the basic formula with the constant growth model to find the stock price. First, calculate each non-constant dividend, D1 through D5. Discount each non-constant dividend at the required return. Calculate the first constant dividend, D6. Use D6 in the constant growth model to find the stock price at time 5. This represents the value of all dividends after the non-constant growth. Discount P5 back 5 years. Sum up all these discounted values to find the current stock price. And we'll see this laid out in detail on the next slide. This is the same problem laid out on a timeline. Places to be very careful. Use D6 to find P5, then discount P5 back 5 years. This is where a lot of mistakes happen. Once you've laid out the values on the timeline, you can use the cash flow worksheet in your calculator to solve for the stock price. Do not forget to add D5 and P5 to create cash flow 5. This example is taken directly from 331 to repeat and reinforce the non-constant growth steps. Placing the values on a timeline. Again, be careful using D4 to find P3. Putting these values in the cash flow worksheet. Again, remember cash flow 3 is equal to price at time 3 plus the dividend at 3. They both occur at time 3. And this example is posted in Blackboard. Going back to bonds, this graph represents the relationship between interest rate and bond value. Basically, the value or the price of a bond is a present value, so when the discount rate goes up, present value goes down. This table and graph demonstrate the impact of a bond's maturity on the volatility of its price. The absolute value of percentage price change is the change when interest rates increase from 7 to 7.5% for bonds with a 6% coupon and different maturities. Note that volatility increases at a decreasing rate, stabilizing at 6.67%. This table and graph demonstrate the impact of a bond's coupon on the volatility of its price. The absolute value of percentage price change when interest rates decrease from 7 to 6.5% for bonds with various coupons but all with 10-year maturity. As the coupon rate goes down, the price volatility goes up since more of the total value of the bond is in the face value. Duration. Duration is defined as shown. The weighted average time to maturity on a financial security. It's measured in years. Duration provides a relatively simple measure of a bond's sensitivity to changes in interest rates. It captures the effect on volatility of both coupon and maturity, which is what we just looked at on those charts. We'll be looking at the duration of bonds paying annual dividends. This is Macaulay duration. If the security makes semi-annual or monthly payments, then the cash flow, the interest rate, and the number of periods must be adjusted to reflect the payment frequency. Look at the formula. D is duration, measured in years. Cash flow at time T is the cash flow for period T, the coupon payments. T is the time, in this case the year of the payment, and R is the yield to maturity of the bond. Put all that together. The denominator is equal to the price of the bond, the sum of the discounted cash flows. The numerator is the sum of each discounted cash flow times T, and we're going to go over several examples. This version of the duration formula simply replaces the denominator with P0, the bond price. Here is a simple 4-year example of computing duration. This bond pays a 10% coupon annually, has a face value of $1,000 and a yield to maturity of 8%. Current price, $1066.24. First, discount each cash flow. The sum of the discounted cash flows by definition is the bond's price. Multiply each discounted cash flow by the year and sum the results. Divide the summed result by the bond price, the result duration. These formulas adjust the basic Macaulay duration formula for more than one interest payment per year. This slide recaps the features of Macaulay duration. First, as the coupon rate increases, duration decreases. Think about it. If duration measures the average time to maturity, the sooner you get the dollars, the less time. As the yield to maturity on a bond increases, the duration decreases. As the yield to maturity increases, the present value of each cash flow, a factor in the numerator, declines, and the price of the bond, the denominator, declines. As the maturity increases, duration increases. It's the opposite of a higher coupon. Longer maturity puts the face value farther in the future, increasing duration. Modified duration is a version of Macaulay duration that estimates the percentage change in bond price for a given change in yield to maturity. Note the negative sign before duration. That indicates the inverse relationship between yield to maturity and bond price. While this addresses using modified duration for a non-annual payer security, note that the annual change in interest rates is plugged into the prediction model. Duration is an accurate predictor of price changes only for very small interest rate changes. For day-to-day fluctuations, duration works quite well, but when interest rates move significantly, such as when the Fed makes an announcement of a rate change, the predicted pricing errors can become significant. The prediction errors arise because bond prices are not linear with respect to interest rates. Convexity describes the nonlinear relationship between bond prices and interest rates. A convexity factor incorporates this nonlinear curvature into the price change calculation. Convexity is a good thing, as it decreases the error in the duration calculations. All fixed income securities are convex. The incorporation of a convexity factor into duration computations is beyond the focus of this class, but it's introduced here to highlight the nonlinear relationship. Let's end Chapter 3 by walking through a duration example. On this slide, in the example, we'll compute Macaulay duration. 5-year bond, 6% coupon paid annually. Yield to maturity is 7%. Predict the new price if annual rates increase by 50 basis points. Rather than discounting each cash flow as we usually do, the textbook examples uses the table factor, which is the same thing. The resulting bond price is $959, Macaulay duration 4.45. Given the Macaulay duration from the previous slide, we can find the modified duration, 4.16. If yield to maturity increases from 7 to 7.5%, using the modified duration formula, we find that the bond price will decline by 2.081%. So the new bond price will be $959 times 1 minus the percentage change in price, $939.05. As proof, we recalculate the bond price using a yield to maturity of 7.5, and we get $939.31. It's pretty close. This ends Chapter 3.